What are Pythagorean triples? Now this term Pythagorean reminds us of the term Pythagoras theorem. In fact, Pythagorean triples and Pythagoras theorem are very closely related, and let's see how. Pythagoras theorem says that if you have a right angled triangle ABC, right angled at B, where A and B are the lengths of the two legs and C is the length of the hypotenuse of this right angled triangle, then A squared plus B squared is equal to C squared. Okay, now you'll ask, how is it related to Pythagorean triples? If we have a set of three positive integers x, y, z, where z is the largest of these three numbers, and if x squared plus y squared is equal to z squared, if this condition gets satisfied, then this is actually pointing towards the Pythagoras theorem. It means that using x, y, and z, these three positive integers as the lengths of the three sides of a right angled triangle, you can form a right angled triangle, something like this. It's a rough diagram, so please ignore the lengths here. So let's say this is z, let's say this is x and this is y, the lengths. So if this condition gets satisfied, x squared plus y squared is equal to z squared, that is, it's pointing towards the Pythagoras theorem. It means that these are actually the three lengths of the sides of a right angled triangle. That is why we say that these Pythagorean triples and Pythagoras theorem, these are closely related, because now these are Pythagorean triples. X, Y, Z, this set is actually Pythagorean triples. Okay. Now, let's look at this table, and this is some small primitive Pythagorean triples. Now, I'm going to explain you what do we mean by this term primitive. We have discussed this Pythagorean triples, but what do we mean by primitive? That's what we have to discuss here. So we have 1, 2, 3, and 4 sets of three positive integers, which we say are Pythagorean triples. It means if you take this one, 3, 4, 5, 3, 4, 5, then 3 squared plus 4 squared should be equal to 5 squared. If you solve it, you get 9 plus 16 should be equal to 25. That is, 25 is equal to 25. Yes, it is a Pythagorean triple. Same if you want to check for this one, this is 5, 12, 13. Now 5 squared plus 12 squared should be equal to 13 squared if these are Pythagorean triples. This is a set of Pythagorean triples. So 25 plus 144 should be equal to 169. So 169 is equal to 169. Yes, the condition gets satisfied. Yes, these are Pythagorean triples. You can check for this one in the same way, and you can check for this one in the same way. Now, you'll ask, what are then primitive Pythagorean triples? If you look at these 4 sets of Pythagorean triples, then you will find that their highest common factor or the greatest common divisor is equal to 1. The highest common factor is equal to 1. That makes them primitive Pythagorean triples. So it'll ask that then what's the opposite of primitive Pythagorean triples? And that's a really very nice question. And the answer is it is imprimitive Pythagorean triples. Imprimitive Pythagorean triples. Let me explain you what do we mean by that. It's just the opposite of primitive Pythagorean triples, that in this case highest common factor or the greatest common divisor will not be equal to 1. In fact, it will be some other positive integer. Okay, so let's take this 3, 4, 5, this Pythagorean triples. Okay, if we multiply this Pythagorean triple by 2, then you get 6, 8 and 10, right? If you multiply this Pythagorean triple by 3, you get 9, 12 and 15. Okay, now these two sets of 3 positive integers, these are 2 different Pythagorean triples that are imprimitive, because in this case actually the highest common factor or the greatest common divisor is now 2, and in this case the highest common factor or the greatest common divisor is now 3, right? It means that from primitive Pythagorean triples you can form as many imprimitive Pythagorean triples. Just simply go on multiplying them with different integers, right? In the same way you can multiply this with 2. So if you multiply this with 2, your Pythagorean triples will become 10, 24 and 26. That is imprimitive one, right? Now if you want to check whether this Pythagorean triple satisfies x squared plus y squared is equal to z squared, then you can check here. So 6 squared means what? 36 plus 64. This should be equal to 100. And if you solve it, you get 100 is equal to 100. So can you see it's actually Pythagorean triples only, but in this case it is imprimitive because the highest common factor is now in this case 2 and not equal to 1. If you want to check for this one, 9 squared is 81 plus 144 and 15 squared is 225. This should be equal to 225. So 81 plus 144 is 225 is equal to 225, right? So yes, these 3 are Pythagorean triples, but since the highest common factor is 3 and not 1, therefore it makes it imprimitive Pythagorean triples. Okay, now you can tell for any positive integer m greater than 1, for greater than 1 you can tell your Pythagorean triples using these 3 algebraic expressions. Let's take m is equal to 2. When m is equal to 2, then your Pythagorean triples will be 4. M square means what? 4. 4 minus 1 is what? 3. M square means 4. 4 plus 1 is 5. Right? Let's take m is equal to 3. So 2 times 3 is 6. Then 3 squared is 9 minus 1 is 8. 3 squared is 9 plus 1 is 10. So this is another Pythagorean triples. Now let's take last one. M is equal to 4. So 2 times 4 is 8. 4 squared is 16 minus 1 is 15. And 4 squared is 16 plus 1 is 17. Right? So in this way we can calculate our Pythagorean triples using these 3 algebraic expressions, but the condition is that your m should always be greater than 1, right? So in the next video tutorial we are going to discuss problems based on Pythagorean triples. We have a problem here. Find a Pythagorean triple in which one member is 12. We know that we can tell Pythagorean triples using these three algebraic expressions, that is 2m, m squared minus 1 and m squared plus 1. If you put different values of m that are greater than 1, all the positive integers that are greater than 1, if you go on putting here, then you'll get different Pythagorean triples. For 2 it will be something else, for 3 it will be something else, so on and so forth. But here it has been given to us that 12 is one of the member of this Pythagorean triple. So let's say that this is x, this is y, this is z. We don't know whether this 12 is x or y or z, right? No worries. Let's assume first assumption that 12 is actually z. It means that m squared plus 1 is equal to 12. Solve it, you get m squared is equal to 11. Okay. If you put m is equal to 3, then you get 9. No, it is not equal to 11. If you put m equal to 4, you get 16. 4 squared means 16. No, again you're not getting 11. It means that if you try to find out the value of m from here, that will not be an integer value. That will not be an integer value. Okay, that will not be an integer, because if you put m is equal to 3, it's giving you 9, and when you put m is equal to 4, it's giving 16. So between 3 and 4, there is no other integer that can satisfy this one. That's why this assumption is wrong. Let's take next assumption, that let this 12 is actually y. It means that m squared minus 1 should be equal to 12. From here, you get m squared is equal to 13. Okay. Now if you put m is equal to 3, you get 9, because 3 squared is 9. You put 4, m is equal to 4, you get again 16. That is not equal to 13. It means again, if you are trying with this assumption, you'll not get the value of m as integer value. It will not be an integer value. Okay, it means even this assumption is wrong. So let's move to the third assumption, that let this 12 is actually x. Let's assume that. It means 2m is equal to 12. Okay. Now from here you get m is equal to 6. If you divide both the LHS and the RHS by 2, you get m is equal to 6. And from here we have got the value of m, that is m is equal to 6. Now simply put it here. So when you put 6 here, you get 12. This 6 here, 36, 6 squared means 36. 36 minus 1 is 35. 6 you will put here. 6 squared means 36 plus 1 is 37. So this is our Pythagorean triple, right? Another one, it is 18. So again, 2m, m squared minus 1, m squared plus 1, right? M should be greater than 1 and it should be positive integer. Okay, let's say that this is x, this is y, this is z. Now one of the member is 18. We don't know whether 18 is x or y or z. Okay, let's assume that 18 is actually m squared plus 1, that is z. So m squared plus 1 is equal to 18. Okay, so m squared gives you what? 17, right? Now when you put m is equal to 4, 4 squared is 16. No, it is not equal to 17. When you put m is equal to 5, you get m squared as 25. No, it is not equal to 17. It means this assumption is wrong. Next assumption will be that let 18 is equal to y. Let's assume this. It means m squared minus 1 is equal to 18. So from here you get m squared is equal to 19. I missed one point here, that if you solve for this one, m will not be an integer value. You have to write this thing. You have to explain each and everything. And why, if you will say that, okay, if it's not an integer value, what if we are getting a decimal value? No, m should be positive integer that should be greater than 1. You cannot take a decimal value. Okay, so m squared is equal to 19. When you put m is equal to 4, you get 16, not equal to 19. When you put m is equal to 5, you get 25, not equal to 19. It means that again this assumption is wrong, because again here you not get the value of m as an integer value. Okay, so last assumption, that 18 is actually x, that is 2m is equal to 18. If you solve it, if you divide both the LHS and RHS by 2, you get m is equal to 9, right? Here we are getting an integer value. Okay, so the value of m is equal to 9. Now put this 9 here. So 2 times m9 is 18. Then m squared means 9 squared 81 minus 1 is 80. 9 squared means 81 plus 1 is 82. So this is the Pythagorean triple in this case, where 18 is actually 2m. Okay, this is the last one. One of the member is 35. Again, you have to remember this: 2m, m squared minus 1 and m squared plus 1. M can only be a positive integer and should be greater than 1. Okay, so let's say that this is x, this is y, this is z. We don't know whether 35 is x or y or z. Let's begin our assumption, and let's assume that this 35 is actually z, that is m squared plus 1 is equal to 35, right? From here you get m squared is equal to 34. Now if you put m is equal to 5 here, you get 25, not equal to 34. If you put m is equal to 6 squared means 36, again not equal to 34. So if you solve for this one, if you solve for the value of m will not be an integer value. And we'll discuss more on this in coming video tutorial, that what happens when you are not actually getting the value of any variable, whether it is m or x or y. It's not integer, but what happens when you get decimal value and how to calculate that. We'll discuss these things in our future video tutorials. Okay, so again, not integer value, so you cannot take this one, because m has to be positive integer and should be greater than 1. Okay, so this assumption is wrong. The next assumption is that 35 is actually y, that is m squared minus 1 should be equal to 35. And if you solve from here, you get m squared is equal to 36. Now you put m is equal to 6 and you get 36. Yes, it's getting satisfied. This condition is true. From here it means that you get m is equal to 6. Now some of you will say that, hey, you know what, we can even take m is equal to minus 6, because minus 6 squared is actually 36. Yes, but the condition is this one. It should be a positive integer and should be greater than 1. Neither it's a positive integer, neither it's greater than 1. Okay, nor it's greater than 1. So m is equal to 6. Okay, this condition gets satisfied in this one. But let's check for this one also, right? It's good to check for this one. So 2m is equal to 35. Again, if you divide both the LHS and the RHS from here, you get by 2, you get 35 by 2. Of course, this is not a, if you solve for this one, you'll not get an integer value for m. This means that this assumption is wrong. Which assumption is correct? This one, that is m is equal to 6. Now if you put this value of m here, you get 12. Then 6 squared is 36 minus 1 is 35. And 6 squared is 36 plus 1 is 37. So this is our Pythagorean triple for this one, where this 35 is actually m squared minus 1. Write a Pythagorean triple whose smallest member is 8. Now we know that we can calculate Pythagorean triples using three algebraic expressions, that is 2m, then m squared minus 1 and m squared plus 1, right? Where m can take any value of a positive integer which should be greater than 1 and should be a positive integer. So this much we know. Okay, since this is a Pythagorean triple, you can go on putting different values of m, like 2, then 3, then 4, then 5, and for each different value of m you'll get different Pythagorean triples, different sets of Pythagorean triple. So let's say that this is x, this is y, and this is z. From this we know that since it is a Pythagorean triple, it means x squared plus y squared is equal to z squared, where z is actually the largest of these three, is the largest one. It means that 2m squared plus m squared minus 1 whole squared, this is equal to m squared plus 1 whole squared. Okay, and this will m squared plus 1, this will give you the largest value of the largest member. So this is asking for the smallest member is 8. It's given that the smallest member is 8. So when we begin our solving this problem using the assumption method that we have discussed in the part 1, that's why I'm saying please watch that tutorial first. In that assumption method, you'll ignore this one, m squared plus 1. That is, you will not check for m squared plus 1 is equal to 8. Why? Because we have already discussed, like from here you can see that this z, that is m squared plus 1, is actually the largest of these three. Therefore, there is no way that z can give this m squared plus 1 will represent the smallest member, right? Okay. So it means that the assumption method will be used in two different ways. The first one is like your m squared minus 1. Let's assume that this is equal to 8. That is, 8 is actually y. Okay, let's assume that 8 is equal to y. So from here, if you solve it, you get m squared is equal to 9. And from here, if you put m is equal to 3, then you get actually m squared is actually 9. For m is equal to 3, this is true. Now some of you will say that, hey, you know what, we can even put m is equal to minus 3, because minus 3 squared is equal to 9. Yes, you are correct, but minus 3 cannot be correct here, will not be correct here, because m can only take values that are greater than 1 and positive integers, right? So this is neither a positive integer nor greater than 1, right? Okay, so m is equal to 3. It means that this assumption is correct. That is, if we assume that m squared minus 1 is equal to 8, then we are getting m is equal to 3. But let's assume that, check for this one also. That is, let's assume that 8 is this 2m. So 2m, that is x, 2m is equal to 8. From here, you get m is equal to 4. Okay, you get m is equal to 4. Now, you'll say that, hey, even we are getting an integer value here, m is equal to 3. And m is equal to 4 is also an integer value. Now, this time we are getting two integer value. Which one is correct? That's why I said that it's important to check this one also. Now, let's take this one. That is, m is equal to 3. So if you take m is equal to 3, and if you try to find out this value, that is 2m, 2m means what? 6. Then 3 squared means 9, minus 1 is 8. And then 3 squared, 9 plus 1 is 10. So the value that you are getting here is 6, 8, 10. Okay, check for this one, that is m is equal to 4. When you put m is equal to 4 here, you get 8. Then m is equal to 4 here means 4 squared is 16 minus 1 is 15. And 4 squared 16 plus 1 is 17. Okay. Now, if you check this one and if you check this one, in this Pythagorean triple, actually 6 is the smallest value. That is 6 is the smallest member and not 8. But if you check this Pythagorean triple, then 8 is the smallest member as per this question. It satisfied this condition. But it means that when you take m equal to 3, then that's actually giving you a Pythagorean triple. But in that Pythagorean triple, 6 is the smallest member and not 8. That is why this assumption is wrong. And that is why it's important to check each and every member, right? Each and every x, y, and z in this case. So you can clearly see here, when we solve for m square minus 1 is equal to 8, and that is we assume that y is equal to 8, and then we assume that x is equal to 8, this assumption is correct because this is giving you whatever is required in this question.